we're talking about varifolds, and we say that a rectifiable varifold is just basically a pair So remember, this was technically this is actually the equivalence class of all possible pairs, where all possible pairs of a set which agrees with M almost everywhere and a function that agrees with theta almost everywhere. But that's sort of like L1 functions, right? That's the way you define L1 functions. They're equivalence classes of functions which agree almost everywhere with each other. So this is the same business as that. So suppose a rectifiable varifold, and we remember this means that this is an Hn measurable, countably n rectifiable set. Contained in Rn plus k. Everything's happening in Rn plus k here. And suppose this is rectifiable. This is a rectifiable varifold, rectifiable n varifold. You should always specify what dimension you're talking about. So rectifiable n varifold, Nu, and this is always an open set. And this theta is positive. Hn almost everywhere on M, and integral over M intersect K of theta dHn is finite for every compact K contained in the set U. So that's what we mean by a rectifiable varifold, and we introduced some notation. We call the measure here mu v is just the measure that you get by integrating over A with respect to theta dHn measure. And we talked about the first variation, and I pointed out that the same formula holds. The first variation was ddt of mu v. You push forward the varifold with respect to restricted to k. That was another bit of notation we used. V restricted to any set A is simply the varifold that you get by taking intersection with A. And we computed this, or rather the measure of this, the total mass of this. That's yet another piece of notation. So the total mass, this is the measure. The total mass of V is the measure of the whole thing. So we computed that, and we found that we could just use exactly the same argument that we used in the C1 submanifold case. So in fact, this turns out, if we do this at t equal to 0, this turns out to be, as long as x is C1 with compact support on the open set U containing where we're working, and with values in Rn plus k. Remember, these are vector fields on the ambient space on Rn plus k. And we found that we could write this as integral over m div sub mx d mu v, or theta dhn if you like. Notice if you want to write it a bit more intrinsically, that would be the integral of div sub mx d mu v. And div sub mx is, as usual, the sum I equals 1 up to n of you take an orthonormal basis and you take the directional derivatives of the vector field x with respect to that orthonormal basis, and you dot with tor, take the sum, and this is div m at a point x. And here tor 1, tor n is an orthonormal basis for the approximate tangent space. Okay, that was good. So that's as far as we got last time. Now, there's an important definition here. We say that the varifold V is stationary in U if this first variation vanishes. Equals 0 for every one of these vector fields. So that's a key definition, and we should relate this back to something we're familiar with. Now remember that we talked about first variation of C2 submanifolds. So recall, if M is a C2, okay.
Thank you.
Yep. For every C1x with support x intersect M compact, in other words, compact support, we proved that that was true. In fact, we proved a general identity. We proved that in general, this quantity is equal to minus the integral of the mean curvature vector of M dotted with x dHn for every such vector field. That was an important identity. It's called the first variation identity. So that's what we know for a smooth submanifold. And where h is the mean curvature, so h equals mean curvature. Remember how that's mean curvature vector. Remember how that was defined. That's just the trace of the second fundamental form. It's the sum from I equals 1 up to n of the second fundamental form of M at x in the directions tor I, or again, tor 1 up to tor n's an orthonormal basis. So it's the trace of the second fundamental form, in other words, basis of Txm. So let's see if we can relate these things now. So here's one definition for a general varifold. We say it's stationary if this quantity is 0, right? For every smooth vector, for every C1 vector field with compact support, right? Whereas for a smooth submanifold, we have that the first variation is equal to this, right? So you see the connection, right? That means that the smooth submanifold, when you give it multiplicity identically 1, is a stationary varifold in this sense, if and only if the mean curvature vector vanishes everywhere. So thus, the varifold V equals the varifold that you get by taking the smooth submanifold M, the C2 submanifold M, together with the multiplicity function 1. So this means theta identically equal to 1 on it. That's stationary if and only if the mean curvature vector is equal to 0 on M, everywhere, identically 0 on M. Now we've got to be a bit careful about supports of things. So this is stationary in the set that you get by taking Rn plus k minus the topological boundary of n. Because we need this condition when we would, here we're assuming that support of x intersect m is compact, so we've got to keep away from the topological boundary of m, otherwise that won't be true, right? So, so delta m equals topological boundary of m. In other words, it's just the closure of m in Rn plus k minus m. Closure of the set M in Rn plus k. So, in other words, this notion that we've got here of stationary rectifiable varifold is simply the natural generalization of C2 submanifolds with 0 mean curvature vector. They are the smooth stationary things. So, by the way, the usual terminology that geometers use for this is M is a minimal submanifold. That would be the terminology that's got, in some ways it's maybe not very good terminology, but it's the one that historically arose and now everyone sticks with it. Minimal, maybe it's not such a bad bit of terminology because it turns out that these smooth things are indeed minimal, at least locally. They're least area, at least locally, when you make a small perturbation which keeps everything outside a small neighborhood fixed. So that's where the terminology comes from. But as far as we're concerned, the important thing is that we should think of stationary rectifiable varifolds as being the natural generalization of smooth minimal submanifolds. Okay, so let's see if we can compute some things about stationary varifolds now. So let's see if we can use this computation. As I mentioned once or twice before, that when you have an identity like this for an arbitrary vector field, you can often get extremely interesting information by making special choices of x and seeing what it gives you. The trick is to choose the right things to plug in there. So let's see if we can do some of that. So let's choose Well, before we even start our choice, let's set things up. So this is all happening in an open set U. So the schematic of this is that we've got this open set U, and M is some rectifiable, n-rectifiable, countably n-rectifiable set in there. Let's take a fixed ball. It doesn't have to be centered on M. It can be centered anywhere. Let's take a fixed ball of radius r, centered at some point xi, and make sure it's contained in our open set U. So take a closed ball contained in U. And now I'm going to pick a particular x. Choose x at x to be equal to, well, I want to make it to be a radial vector radial from this point as origin. So I want to take x, multiples of x minus xi. Now I'd like to take that as my choice of x, but of course that's not correct. X has to have compact support, right? So we've got to put a function in front of it which gives it compact support. So let's take the simplest kind of choice you can. That is a function gamma of just the variable r, where r is the length of this guy. And let's agree that a gamma looks like this. Something like that. Where, so it's a decreasing function. It's identically 1 in the interval 0 rho. Now that, as long as rho plus epsilon is less than r, that will make sure this has compact support. So this is a correct function to plug in there. Okay, so let's compute. So div sub m of x. Well, you remember we had a couple of ways of computing that. The simplest way in this case is simply to use the formula using the orthogonal projection matrix for the approximate tangent space. So that formula would be the sum ij equals 1 up to n plus k. And then it's eij dixj, the ith partial derivative of the jth component of x, evaluated at x, where eij is the matrix of the orthogonal projection onto the approximate tangent space of M. Remember, in terms of an orthonormal basis, that's just given by the sum L equals 1 up to n of tor Li tor Lj. But so it's an n plus k by n plus k matrix. So this sum goes from 1 up to n plus k. And now we just have to compute these derivatives. See how this works out. Well, let's see. I think we already did this. We already did this once when we were talking about just this vector field. When you differentiate, when you take the ith partial of the jth component of this part, that just gives you the Kronecker delta ij, right? So this is, so that when you differentiate that bit, you get, we're leaving gamma alone for the moment, so that's just sum ij equals 1 up to n plus k, Kronecker delta ij times eij. That bit. And then when we differentiate the gamma prime bit, notice that di of gamma r by the chain rule is just gamma primed r times the ith partial derivative of the radial of the distance function. Now the ith partial derivative of the distance function is just xi minus xi over r, because this is the square root of the sum of squares. like so. So you get this formula. So that's good. We can plug that in. So then we get a gamma primed R sum ij was 1 up to n plus k. Now we already had an xj minus xij, and now we've also got an xi minus xi. So we have x, maybe I should use superscripts here for points. That's what we've been doing so far, so let's stick to that. So that's xj minus xij, xi minus xi times xj minus xij, and then sum eij, and this is over r squared, but actually it was just over r to the first power, so I've got to correct that r squared by putting a factor of r out the front there. So that's what you get for the computation, and of course this just gives you the trace of eij. Now eij is an orthogonal projection onto an n-dimensional subspace. So as we mentioned before, if you take the trace of an orthogonal projection onto an n-dimensional subspace, you just get the number n, right? So this is gamma r n, so it's n times gamma r, that's just identically n. So this guy's identically equal to n, the dimension. So that's just n times gamma r plus r times gamma primed r times this quadratic form. Now, again, eij is the matrix of the orthogonal projection onto the approximate tangent space. So this is simply the length of the orthogonal projection of the unit vector x minus xi over r squared. And remember that this unit vector, see this here? That means that the full gradient is that thing, x minus xi over r. So that's the full gradient. So this can also be written as the orthogonal projection of the full gradient of r, but that's the tangential gradient on M of r, right? So another way to write this guy can alternatively be written as length of the tangential gradient of r squared. So there's a couple of nice ways of writing that term. Okay, so let's go back now and plug that in to the first variation formula. That's this thing here. See what happens. Well, it's good to make a little analytic trick before you actually do that computation. I'm going to use an analytic trick here. So at the moment, this is valid as long as gamma. This is valid so far for any gamma which vanishes as long as you vanish for r bigger than r, because we need to have compact support. So far there's been no restriction on gamma. Now I'm going to make a rather special choice. I'm going to take a fixed function phi, which is going to be C1 or C infinity, if you like, with compact support on Rn plus k rather. And phi is going to actually be a radial function, so phi is, yeah, in fact, let's write it that way. Stupid. Let's write phi in C infinity on the real line. And I want it to have the property that it's identically 1. Here's the origin. Here's the point 1. I want it to be identically 1 on the unit interval 0, 1, and to go down to 0 by the time you get out to radius 1 plus epsilon. take any such function. It doesn't matter. It's got to be decreasing, but otherwise anything. So decreasing, C infinity. And then I'm going to choose gamma in our identity, in that identity over there. I'm going to take gamma of R. One other thing before I do that. There's also a scaled version of phi. This is a standard trick. There's a scaled version if you take phi of R over rho. What does that look like? This is what the graph of phi R looks like. What does the graph of phi R over rho look like? Well, it looks the same, except that it does, instead of 0 to 1 to 1 plus epsilon, it's 0 to rho to 1 plus epsilon times rho, right? So it'll look, if rho is small, it'll be sort of scrunched up like this. So this will be rho, and this will be 1 plus epsilon times rho. So that's what, this is the graph of phi R over rho. So that's what I'm going to choose for gamma. I'm going to take a rho less than R. In fact, I want rho times 1 plus epsilon to be less than R, because I want to, again, make sure our function that we plug in has got compact support. So I want that to be less than R. And rho positive, of course. So I'm going to plug in, so take gamma of R equals phi of R over rho. You'll see why we do this in just a second. So then we want to work out this expression in that case. Okay, in particular, I want to work out this quantity, R times gamma primed R, for that choice. Well, notice that that tells us that R times gamma primed R is phi primed, R times phi primed 1 over rho. The chain rule gives you phi prime times 1 over rho, right? So this will be equal to R over rho times phi prime of R over rho. And notice that that is the same as, this is actually a nice trick, that's the same as minus the derivative with respect to the parameter rho of phi R over rho. Check that. By the chain rule, dd rho of that quantity is phi primed R over rho, and then you've got to differentiate R over rho with respect to rho. That gives you a, oh, sorry, that's wrong, isn't it? It's minus rho times that. Let's try again. So we've got to differentiate that quantity with respect to rho. By the chain rule, that gives us phi primed R over rho times the derivative of R over rho with respect to rho, which is minus R over rho squared. And we get back, the minuses cancel, and we get back to R over rho. So that's correct. So now let's plug that in. So then, now let's see, we're using this identity, and we've computed div mx right here. It's equal to this. So we've just got to plug this in with our new choice of gamma. So we get n times integral. For gamma, we've got phi R over rho, d mu v. And then we've got a minus sign coming from here, and it's rho times dd rho, phi R over rho, times the orthogonal projection times the grad m R squared. Write it that way. That's all. And so it's n times minus rho times the integral d mu v equals 0. So that looks messy enough, but you'll see in a second that everything actually turns out rather nicely in just a minute. All right, let's see if we can rearrange this a little bit. That's, so let's leave this term. Notice that this one you can pull the dd rho outside because everything is C1 here. And fixed L1 functions, so no problem. Using difference quotients and the Lebesgue-dominated convergence theorem, it's easy to justify pulling out the derivative. So this can be rewritten as n, let's agree on the notation. I rho, let's let I rho be this guy. Mu v. Then since we can pull that out there, this is just the derivative of that, except that it's got this guy here. So let's observe that I can rewrite this guy as 1 minus the orthogonal, now let's see, originally it was the orthogonal projection onto the tangent space, and this is a unit vector in Rn plus k. So this expression is also equal to 1 minus the length of the orthogonal projection onto the normal space of that unit vector. So we can rewrite the thing that way. So I get, I can rewrite this part of it. I can rewrite as 1 minus the orthogonal projection onto the normal space, perp, of the unit vector x minus xi over r squared. So that, we can do that. So let me take the 1, the part of the integral involving the 1 here, and that gives me, so we get n times, this is n times I rho in our new notation, so this is n times I rho. And then from this 1 we get a derivative of I rho, so it's minus rho times I primed rho. That's the derivative. Remember, you can pull the derivative outside, so that's I primed rho. And then the remaining term is this guy, plus, so I can put that onto the other side. Let's see, it's got a plus on this side, so it'll have a minus on the other side. So minus rho times dd rho of the integral of phi r over rho times ptxm perp. It's the orthogonal projection onto the normal space of the unit vector uv. So we get that identity. So that's starting to look a little better. Still looks like a big mess, but not such a bad mess as it did a second ago. And now the people that know some ODE theory will recognize immediately that you can write this as an exact derivative. Exact derivative, that's right. If you multiply through by rho to the minus n minus 1. So you can rewrite this as, so you multiply through by rho to the minus n minus 1. And you can rewrite this as dd rho, rho to the minus n I rho. Let's see, there's a minus sign now because when I differentiate, let's see, no, yeah, that's right. When I differentiate this, I get a minus n, so I've got to correct that. But otherwise, it's correct. Right, yeah, that's right. Equals, let's see, did I get the powers right though? This is why I've got to multiply by rho, right? Thanks. That's right, rho. So that takes care of that, and this term is, let's say we're doing rho to the minus n minus 1, so minus rho to the minus n minus 1, but yeah. Rho to the minus n, I think, isn't it? Let's see, this is, when we differentiate this out, we get rho to the minus, oh. Did I do the wrong thing there? Right. Yeah, I think it's, if we if we leave this as, I think that's right now, right? If we just leave a rho to the minus n there. And let's check it in a second. Let me do it. Actually, on this side, it's better to leave dd rho inside, and I'm going to do that rather than pulling it out. So let's leave the dd rho inside the integral on this side. Okay, so this is, I claim that you get rho to the minus n here, and I'm leaving dd rho on the inside of this integral. Could pull it out, but it's better to leave it inside for the moment. Times the sky, dtxm perp x minus psi over r squared d mu v. Now let me check that I did that right. So when we differentiate this, we get a rho to the minus n minus 1, and I had, okay, rho to the minus n minus 1. Yeah, I would get that when I multiply through by rho to the minus n minus 1. Yeah, so that's correct. That's the correct expression. Except that, did I get the sign right? I think so, yeah. Yeah. Did I do it right, Joe? That's correct, I think. Okay, so you get that expression. Now, there's a nice thing here that this guy, let's take a bit closer look at that guy. Notice that dd rho of phi r over rho, that is not equal to 0. Only between these two values, rho and 1 plus epsilon times rho. When r is between rho and 1 plus, see, it's 0 otherwise, because the thing's identically 1. Phi is identically 1. This is identically 1. Likewise here, it's identically 1 there, so that has 0 derivative there, and it has 0 derivative there, obviously, since it's 0. And so the only place it's got non-zero derivatives between rho and 1 plus epsilon times rho. One plus epsilon times rho. Okay, that's good, because that means we can bound this term now. So we get dd rho, rho to the minus n, I rho is less than or equal to. Now let's see. If I put the rho to the minus n inside the integral, of course I can do that because rho is just a constant. We're not integrating, we're integrating with respect to x here. So that's rho is just a constant. But rho inside the integral is less than or equal to 1 over r. See, 1 over rho is 1 over r is less than or equal to 1 over rho. So since r is bigger than or equal to rho. So we can say that this is certainly less than or equal to integral, now with the thing inside the integral, r to the minus n. Instead of rho to the minus n outside, I put r to the minus n inside. And everything else is the same, dd rho phi r over rho. Times this orthogonal projection onto the normal space. X minus psi over r squared, d mu v. So we have that. And it's also bigger than or equal to a similar expression, except we're out by a factor 1 plus epsilon, and we're doing the nth power. So it'll be out by a factor 1 over 1 plus epsilon to the nth power on the other side. So we'll get integral 1 over 1 plus epsilon to the nth power, integral r to the minus n, again dd rho, phi r over rho. By the way, notice that that's non-negative because phi is a decreasing function of r, but that 4 is an increasing function of rho, right? So this term looks sort of negative, but actually bigger than or equal to 0. So I'm doing the right thing with the inequalities. Likewise. Yeah. Yes. No. It's R is less than or equal to rho. So 1 over R is bigger than or equal to 1 over 1 plus epsilon rho, right? Yeah, so that's correct equality, right? You with me? Remember, this is non-negative, so the inequalities are not being reversed here. There's correct inequality. Yeah, rho to the minus m, that's right. 1 over r is bigger than or equal to 1 over, where this is non-zero, 1 over r is bigger than or equal to 1 over 1 plus epsilon times rho, right? Oh, this one you're talking about. Yeah. And what are you worried about there? Well, I didn't do anything to this term, though. I only dealt with this term.
Yeah, maybe would you replace the term rho to minus n power?
No, I didn't. I've left this term alone.
So the derivative is negative.
What?
The derivative is negative, so we revert this sign.
Well, this is plus, right? Yeah. Right. No, I think you'll see that it's correct. It's okay. So we get this. For every rho with 1 plus epsilon less than, rho times 1 plus epsilon less than r. Okay. And now let's just call this guy j of rho. So let's let j. So we've got our I of rho here, and let's agree to call j of rho. Similarly, this guy without the derivative. So that's integral r to the minus n phi r over rho d mu v times the. Oh, sorry, I've left off the ptxm perp x minus psi over r squared, length of ptxm perp, this guy. So that's what this integral is, ptxm perp x minus psi over r squared, d mu v. So then what does this say? This says that 1 over 1 plus epsilon to the n times j primed rho, because again, you can pull the integral, you can pull the partial derivative outside the integral. J primed rho is less than or equal to dd rho, rho to the minus n I rho, less than or equal to j prime rho. And that's for rho times 1 plus epsilon less than r, bigger than 0. Okay. Okay, so let's just integrate this now. Everything's C1 here, so we can just integrate. So integrate from sigma to rho. And this gives us 1 over 1 plus epsilon to the n. Now when I integrate here, of course I just get the difference. We've got an r to the minus n, and we get phi r over rho minus phi sigma over rho. And we've got this pt orthogonal projection onto the normal space. Unit vector d mu v is less than or equal to I rho over rho to the n minus I sigma over sigma to the n, and that is less than or equal to the same thing here that we had here, same quantity, but without the extra factor. So r to the minus n phi r over rho minus phi sigma over rho. Oh, r over sigma. Did I do that here? Sorry. R over sigma. And I rho minus I sigma, that's correct. And we've again got this orthogonal projection onto the normal space. D mu v. So that's what you get when you integrate.
Yeah.
Yes?
I agree with this difference. I think here this 1 plus epsilon to the n
Yeah.
should be the other side, and it's
Oh, you mean 1 plus epsilon to the plus
yeah,
n.
because 1 over r is should be.
No. Yes, you're right. 1 over r. No, 1 over r. Oh, you're right. Yeah. Sorry. Oh, I see. Right. So this should have been 1 plus epsilon to the n. Yes. Sorry. Oh, apologies. I should know when to listen to you. When you're that insistent, I must know you're correct. Okay, sorry. Of course, it's not going to matter because we're going to let epsilon tend to 0 right now. Okay, so let's let epsilon tend to 0. Then notice that phi, as epsilon tends to 0, phi r over rho tends to, point-wise, tends to the indicator function of the ball of radius r, centered at xi. Point-wise everywhere, no exceptional points. It decreases to the indicator function of the closed ball, right? Decreases to that. Here it is here. Notice as epsilon tends to 0, you get exactly the indicator function of this closed interval. No exceptional points. That's important because what's a set of measure 0 on this line needn't correspond to a set of measure 0 when we're intersecting with balls up in the n-dimensional space. So it's rather important. Okay, so then what does this tell us? This tells us, let's see. Let's work on this first. So this becomes just the integral over the ball of radius rho, the measure of the ball of radius rho, this guy. So we get the measure, ball of radius rho. So we get the measure of the ball of radius rho centered at xi over rho to the n minus the measure of the ball of radius sigma centered at xi over sigma to the n is less than or equal to, well, in fact, equal to, you get the same limits here, both sides, as epsilon tends to 0, so it's equal to, becomes an exact identity, equals this guy, integral r to the minus n times integral over the annular region between b rho and b sigma of this funny looking orthogonal projection onto the normal space of the unit vector x minus psi over r squared d mu v. That's the monotonicity identity. Monotonicity identity. Okay, let's take a break and I'll tell you more about that after the break. 1 over r, 1 over rho. Very difficult.
How come you count the time so accurate? Every time when you pick one, you count the time.
No, I just pick about 10 minutes to go, I can see a good spot that I might get to. I don't know in advance what that will be, but about 10 minutes away, I can tell which spot it will be.
Okay.
And I aim for that. Yeah.
So I'm thinking, how about the schedule for the how about we put 3 talks? Because one constraint that Mao-Pei, he has class
Yes.
on Thursday and
Yes.
Tuesday
Yes.
from
Yeah.
1:20 to 3
Right.
to 3:10, and I have class on Wednesday. So I'm thinking that probably we schedule 3 talks from 10 to 11 and the break 30 minutes break. 11:30 to 12:30, and then in the afternoon from 12:30 to 3:30.
Okay.
In that way, I do not need
Yeah.
to skip any lecture.
Right. So we have 3 talks the first day,
I mean, 3 talk every day.
every day. 9 talks in total. That's not too bad.
So I'm thinking that probably have Robert in, I'll have Bob in this first day.
Yes.
Probably Brian.
Brian's going to get here a couple of days earlier, right?
Just he will arrive 6.
Yeah, that should be okay then. He's had a couple of days to recover.
And Nami is from Korea.
Yeah,
It's
he's no
easier.
problem. Yeah.
Yeah. So and then the second day, so either Nissan,
Yes.
Rick, and Zhong, my colleague.
Yep.
He can only arrive on this day.
Okay.
And then the third day, Nissan, Johnny, Daniel.
Yeah, that looks good.
Oh, you think it probably is? Would it be better to put the Nissans talk together or separate?
Separate, I think.
Okay,
Yeah.
separate.
Give him a chance to see how he's going in the first lecture before he gives the second one.
And probably we just say we have discussion after 3:30.
Yes.
And probably have a conference dinner
Yes.
on the 9th.
On the 9th. Sounds good.
But on Monday,
No, not Monday. This is Tuesday.
sorry, Tuesday.
Yeah.
On Tuesday, in the morning, I have to attend one of the big conference held by my department. They said I have to be there.
So when will be that?
It's on Tuesday, on the 8th of May.
Yeah, what time?
So it's good. I think I should be able to be back. I don't know. Let's see. Maybe let's say 10 or 10:30. So it's better.
So- Right, so why don't we put Brian first? You want to see Robert, right? You want to see his talk.
Okay.
So you want to see Bob Hart, of course. So why not put Brian first then?
Okay.
Do you?
Yeah, but in general, you want to start at
So if
10, right?
Yeah, can.
So no, the other thing I worry about is sometimes I have a meeting, a department meeting around noontime, but of course I will try to get them away for these 3 days. But if it's impossible to get rid of those, I mean, say from 20. So if we have can we shift the schedule
so
to the afternoon?
if
So
in that
only
case,
in the
I mean,
morning.
one talk in the morning and 2 in the afternoon?
yeah, that
How
certainly
about
is, but that means that then we need to. So for me and the Mao-Pei, we need to skip some class. So. So originally another good thing would be 11 to 12, but in the afternoon, when can you start? Because in the afternoon we need to start at least from 2. From 2, then that means probably still okay. No. Yeah, because, let me see. Okay, let me see. If 10:30 to 11:30. No, and let's practice from 3:30 to 4:30. And that would be Okay, then probably we can also do that.
That might be better. So we would just have one talk each morning, right?
Okay, in that situation, okay, I can rearrange. I rearrange a little bit of my class because my class finish at 2:20. Okay, and in this situation, Mao-Pei also just keep this one.
Will that work though? Are you able to do that?
Yeah. Okay.
Can you do that though?
Yeah.
Without?
Yeah. Okay.
What about Mao-Pei?
But Mao-Pei definitely he needed to split 2 talks, so I
Okay.
already on purpose. I mean for so I can reschedule it. So probably Nami and then he's skip there.
Right.
Okay.
Maybe we should discuss it a bit more after.
Professor Simon, do you
Yes.
you ready?
I think we'd better leave everything today.
Yeah, great.
Okay. That's better. 啊，对了，你的学生证好像在那个。
How many did we get today, Joe?
对，你有一个学生证，我前几天上礼拜看到。
Okay.
在西板。啊。
哦，好，我已经不好意思报很久了。
你疑似报很久了。
李荣宪有美国手面拿好，我去拿我的作业。
Maybe 11.
少一页。
Probably, or it would be even better because the
我以为手上拿是我作业。
probably this break will be too long. Maybe from 11 to 12, and from 2 to 3, 3:30 to 4:30.
Okay. Well, but how does that work out with your lecture schedule?
With my lecture, so I maybe I just tell a student that so yes, so I can just arrange my class. So let the TA to discuss with them somehow, or we just finish early.
Okay. So we go to 11 to 12, have lunch.
To 12,
Oh,
and
and
then 2
Yeah, that's good. Okay. That sounds good.
3:30 to 4:30.
Yep. I see. Okay, so let's continue. So this is our monotonicity identity, and it says quite a few things already. This term is a little bit cumbersome to keep writing this way, so I'm going to abbreviate it using a slightly different notation. I'm going to rewrite this as B rho. It's the integral over the annular region between the two balls, r to the minus n. And then now notice this is the full gradient in Rn plus k of the radial distance, r. And this is the orthogonal projection onto the normal space at x. So a good notation for that would be simply d perp of r squared mu v. So d perp of r means the orthogonal projection onto the normal space of dr, which is this. Remember, dr is x minus xi over r. So this is the same as pt xm perp x minus psi over r. Okay, so that's good. Now let's talk about some consequences of this identity. Remember, in order to get this, we had to assume that the varifold was stationary in the stationary rectifiable varifold in the open set U. Notice, by the way, that xi doesn't have to be a point in the set M or anything like that. This is for every, let's see, we derive this, notice, for every ball B rho xi containing d sigma xi, so sigma less than rho, contained and contained in BR xi, contained in U. So it's completely general. The only restrictions are this, and of course that the varifold must be stationary in U, meaning 0 first variation. So they're the conditions. And under those circumstances, we have this identity. Okay, so notice that this means in particular that this ratio is an increasing function. This side is non-negative, notice. Bigger than or equal to 0. So that means, so then mu v b rho xi over, now it's better to normalize this with the usual factor omega n, the volume of the unit ball in Rn. So let's do that. And we mustn't forget there's a factor of 1 over omega n there in that case. Okay, so let's agree on that. And then notice that this says then that this quantity is increasing function of rho. And of course it's non-negative. Rho bigger than 0, less than r. Increasing in rho. Now in particular that means it has a limit. Finite limit. Some finite non-negative limit exists, and it's somewhere in the interval, could be 0, but it's certainly finite because it's decreasing. So now remember, this is exactly what we called the density, the n-dimensional density of the measure mu v at the point xi. So that's the first thing about stationary varifolds. The densities exist at every point. Exists and is finite for every xi in U. Second thing is that I claim that this density is actually an upper semi-continuous function. Let's check that. This is a good example of an argument that you'll see quite a lot in various contexts of geometric analysis. Where you have monotonicity playing a role, you'll often find upper semi-continuous functions floating around, which are quite useful. So the claim is theta n mu psi mu v xi is an upper semi-continuous function of xi. In the open set U. In other words, that is theta n mu v xi is always bigger than or equal to the lim sup as eta tends to xi of theta n mu v eta. So let's check that. Okay, so let's take an arbitrary ball to begin with. And take an arbitrary sequence of points, psi j converging to xi. Then, and let epsilon be bigger than 0, in fact between 0 and rho. And notice that the ball, for sufficiently large j, the ball of radius rho minus epsilon, centered at xi j, is of course contained in the ball of radius rho, centered at xi. Trivially, this is for sufficiently large j, for j large enough. In fact, as soon as mod xi j minus xi is less than epsilon, less than rho minus epsilon, this will, well, whatever. Certainly true. Okay, so that's good. That's a nice inclusion. So the measures then behave accordingly. Rho. Right. J large enough. And let's see, now divide by omega n times rho minus epsilon to the n. And notice by monotonicity, this is bigger than or equal to the, remember this decreases. As rho decreases, this is an increasing function of rho, but as rho decreases, this decreases down. So this is bigger than or equal to the density at the center point. And for j large enough. So, yeah, so then, so in other words, theta n, so lim sup as j tends to infinity of this, mu sub v xi j is less than or equal to mu v p rho xi over omega n rho minus epsilon to the n. And that's true for every epsilon bigger than 0. So just let epsilon tend to 0. Now we've already used epsilon, forget about it now. And then this tells us that this is less, implies that this guy, lim sup, j tends to infinity of the densities at psi j less than or equal to mu v p rho xi over omega n rho to the n. But that's true for every rho bigger than 0, for every rho less than r. For every rho, let's suppose this is same setup that we had before. That's all contained in a fixed ball. So this is true for every rho, no matter how small. And notice this tends to the density at xi. As rho goes down to 0. So that's it. It's upper semi-continuous. So we've proved this. Okay, that's a very nice fact now, because we can now, for example, give a sort of a canonical representative for the varifold v equals v m theta Namely, yeah, I don't think I've mentioned before that, well, before I do that canonical thing, let me make one further point about this density. Of course, it's not surprising. I mean, look at the definition of it. Here it is here. It's the limit of the density ratio. So pretty clear that that's got to be equal to small theta almost everywhere, right? I mean, let's remember what this is. This says theta n mu v xi is equal to limit, rho goes down to 0, of the measure, that is integral over m intersect b rho xi, theta dhn. That's what our measure is, over omega n rho to the n. And the claim is that that's, of course, equal to, this is equal to theta xi for hn almost every xi. Or another way of saying that, it's equal to theta xi for mu v almost every xi in u. Same statement. Because remember, d mu v is just theta dhn. And that's very easy to check. You'll find the argument that I'm getting a bit behind schedule, so I'd better not do that one. It's an easy consequence of Lusin's theorem and an elementary argument using the fact that we've already proved that the approximate tangent space exists almost everywhere. You'll find this in the text. So let's take that as given. So that means, so now we can choose a canonical representative for this verifold. Remember, this is an equivalence class where you can use any other selection of m and theta as long as they agree almost everywhere with these two, right? So a nice canonical representative is to use v equals v and then s capital theta, where capital theta is just the density. It's the upper semi-continuous function. Capital theta at xi is the mu sub v xi. So you can use that instead as instead of theta. Notice that is theta almost everywhere. That's what we've said here. So that agrees almost everywhere. And then for S, you can let S to be simply the set of points where this is positive. Theta x. Or maybe stick to this notation, set of xi in U, such that theta xi is strictly positive. So that's a nice canonical representation for the way, and that has some nice properties. In particular, if theta is bigger than or equal to 1, hn almost everywhere. That's our original representation. If theta is bigger than or equal to 1, hn almost everywhere on m, then notice, of course, since theta agrees with, capital theta agrees with a little theta almost everywhere, and it's an upper semi-continuous function, that would mean that theta is bigger than, is bigger than or equal to 1 everywhere in the support of v, support of mu v. So, you see, that means that this set S then would be the same as the set of xi in U. This is provided we do have this. provided we do have this, then this is the same as the set of the set of xi and u such that theta xi is bigger than or equal to 1. But that's a closed set, relatively closed in u. So in that, if you do have a lower bound like this, notice this would work if you had any other positive lower bound. The same thing would work. But in particular, if you've got a lower bound of 1, then your canonical representative of S that we're using here would actually be this guy, which is a closed set. It's the same as the support of mu v in U. So this is really a nice way to represent the varifold. As long as you've got a lower bound on theta, then you get a nice closed set to represent your, rather than a sort of arbitrary, rather sort of potentially nasty looking countably rectifiable set. At least you've got a closed set. Okay, so let's see, what else do I need to mention here? Yeah, well, I should mention this notion of stationarity. So far, we've just talked about stationarity in Rn plus k. Now, in geometry, you often want to talk about stationarity in a bigger manifold, in an ambient manifold. So let's consider a more general situation. Suppose that we've got a big manifold n of dimension, say, n plus L, and this is all sitting in Rn plus k still. So everything's still in Rn plus k, but now we've got a big manifold. Suppose this is C2. And suppose our M that we're talking about is contained in, so M contained in N. So V is now a varifold M theta with M contained in N, rather than M contained in an open subset of Rn plus 1. We're now looking at the case when M is a subset of a higher dimensional manifold. And we should make clear what we mean by stationarity in this case. So definition, V is stationary. By the way, notice that this is still a rectifiable varifold in Rn plus k because n is in Rn plus k. But we're thinking of it this way now. So V is stationary in n if the first variation, that is integral, so this is the first variation, same computation, div sub m x d mu v is equal to 0. But now we only require this to hold if for all vector fields x which are tangent to n, rather than arbitrary, or rather than all vector fields. And so this is for every x which is C1 with compact support in n with values in Rn plus k, such that, so these should be tangent vector fields, so such that x at x is in the tangent space of n for every x at least for almost every x anyway, for almost every x in M. So that would be the natural definition of stationarity if we're talking about rectifiable varifolds that are living in N rather than living in an open subset of the Euclidean space. Now remember, that makes sense because remember we did this once before. We checked, we did it in the smooth case, but the same argument works in this setting where M is just rectifiable. We checked that this is indeed the same as d dt evaluated at t equal to 0 of the first variation is the same as mu v of first variation. So it's phi t sharp of v, mass of that phi t sharp of v. Remember that what this is exactly the same as this looks complicated, but it's not. It's v is this guy, so phi t sharp of v is just the push forward of the varifold. It's the varifold that you get by taking the image of m and theta composite with phi t to the minus 1. And here we have the usual conditions on phi t. So phi 0x should be identically equal to x for every x in n. So we're working in n now rather than in the Euclidean space. And phi t x should be equal to x for every x in n minus k for some compact k, and for every t in some small interval of the origin, say minus epsilon epsilon, so usual conditions. We did discuss this before, actually, at least in the smooth case. And the other condition is that this all has to be C1, and phi t is a map from n to n, so it leaves n invariant. Now remember, we talked about this, one of the ways you can achieve that, and the other thing is we should have the x should be the initial velocity vector. That's the other thing. So let's say that. So x at x equals partial dt at t equal to 0 of phi tx. So that's the initial velocity vector. Now notice that then, because phi t is mapping n back into n, this will indeed be tangent. So that's certainly one, so you can interpret this that way. So that this condition is simply saying that the first variation is 0 when you only allow variations which leave n invariant, right? So that seems to be the right definition. Now, so that's the generalization of the notion of first variation to this more general case when you're working in a submanifold instead of in an open subset of the Euclidean space. Now, on the other hand, that's not so convenient because, you see, how are we going to use that? You see, this condition is not convenient at all. Because, for instance, we can no longer do this. We can no longer, remember, to prove the monotonicity formula, we chose x at x to be equal to a certain function of r times x minus psi. Well, that doesn't make sense anymore because this is not tangent to the big manifold, you see. So we can't do that anymore. So this looks extremely inconvenient. But there is a way around that. Namely, let's see what this implies about a general vector field. So with any x, with any C1x with components x1 up to xn plus k, we can always, with compact support, with support x intersect n equal to a compact subset, with any x, you can always decompose x as the tangential part relative to n plus the normal part relative to n. And we can do that for every x in n. And here t in perp means orthogonal projection onto the tangent space and onto the normal space, respectively of n now. Now we did this computation, so then div integral over m of div mx d mu v, that's this guy. Well, that's 0, we're assuming. And that's equal to the div of that plus the div of that. Now, integral over m of div x, oh, sorry, this is not 0 because we're no longer assuming that x, we're not assuming this condition anymore. So we don't know what this is. But we know that this bit, div sub m xt, we know that this bit is 0. That's what we're assuming, because this bit is tangent to n. So that bit goes away, and we just got the normal part. So we've got the integral div sub x perp, div sub mx perp. Now, I think we did this computation, but let me just repeat it since it was a while back. Let's compute div x perp. So div sub m of x perp. This is perp relative to the submanifold n. Okay, well, how do we compute that? Well, that's by definition the sum I equals 1 up to n d tor I dotted with the directional derivative of the vector field of this vector field x. Now, what is x perp? Well, locally, we've discussed this before. Locally, you can write that as the sum over an orthonormal basis of the normal space to n. So you take ortho, so I'm going to let nu 1 up to nu k be an orthonormal basis. For the normal space. That's Txn perp. So we're talking about the manifold n now. That's a C2 manifold, remember? So take an orthonormal basis. Let's see, what's k here? N is n plus L dimensional contained in n plus k. So, so that's k minus L, isn't it? The codimension of n in the space Rn plus k is k minus L. K minus L dimension. That's the correct thing. So it's alpha equals 1 up to up to k minus L, and then you take nu alpha dotted with x times nu alpha. So that's what we have to put in up here. So this is the sum. Alpha equals 1 up to k minus L, nu alpha dotted with x times nu alpha. Remember, as we discussed before, since n is a C2 submanifold, we can at least locally choose these orthonormal vector fields so that they're smooth, at least C1 in a neighborhood of any given point. You can choose these things. They exist. You can use local coordinate representations of n to get these things. Okay, so what is this? Well, let's see. I've got to differentiate, take directional derivative of that bit, but that we can forget about because when I differentiate this bit, I've still got a nu alpha which dots with the tor I to give 0 because tor 1 up to tor n is an orthonormal basis of these of T sub xm, which is contained in T sub xn by definition. So we don't have to worry about those guys, they're 0. So we only have to differentiate these guys. So this is the sum I equals 1 up to n, tor I dotted with, let's do the sum, pull the sum out here. Alpha equals 1 up to k minus L, nu alpha dot x times d tor I nu alpha. And that we recognize, right, that is minus the second fundamental form of n. This is, by definition, we're summing over a basis of the normal space of n, so that by definition this gives us minus, there's always a minus sign, remember, x dotted with the second fundamental form of n. So this is the second fundamental form. Of n, C2 submanifold. Evaluated at tor I, oops, I forgot the tor, I've got to dot this with tor I. Tor I dot that, so this is tor I dotted with d tor I nu alpha. Okay, so that's the second fundamental form, tor I. And we're summing from I equals 1 up to n. Now, it would be tempting to think that, oh, that's the mean curvature vector, but of course we're only summing over an orthonormal basis of the Txm, which is a subspace of Txn. So this is not that. It's a vector field. It's a vector function, but it's not the mean curvature vector. It's in fact we should give it a name. Let's call it HNM. It's sort of a partial trace over the subspace Txm. So it's minus x dotted with HNM. So that means we can plug that in over here. So this is, so we get that for an arbitrary vector field, we get exactly minus the integral of div sub m x sorry, we've computed it. So it's a minus x dotted with HNM, this partial trace. So that's the expression. And now x is again an arbitrary vector field. This is for every x which is C1 compact support in Rn plus k with value in Rn plus k with support x intersect n compact. That's the condition, because that was the condition that we had to begin with here. We needed compact support in n. So now we can indeed repeat all of the first variation computation. We can do this business again. We can plug in vector fields the way we did before. We can plug in gamma of r times x minus I and so on. So let's see what happens when we do that. So take x exactly as we did before. So we're taking gamma of r times x minus I, but gamma is going to be this guy. So take x equals phi r over rho times x minus I, and compute div sub mx as before. Same computation. That doesn't change, because now there is no restriction on we've gotten rid of the restriction. See, we no longer have that restriction. So same computation as before. Okay, well, what happens? Well, you get the same identity like this. Same identity that we had in the case when we were working with stationary submanifolds on an open set. So we'll get exactly the same expression on the left side. squared d mu v. Except that now, instead of that being equal to 0, we've now got an extra term on the right-hand side. And in fact, the term on the right-hand side is a phi r over rho times h, thing that we're calling HNM. It's the partial trace of the second fundamental form of n. So we just have to take care of that term. Now, I won't give all the details, but you can easily, you can check the text, and I'll just show you what you actually get here. What you end up with is, well, you can sort of see how this works out. Notice this h is a partial trace, so h and m sum I equals 1 up to n, the second fundamental form of n, but evaluated it on the orthonormal basis of txm. So this is this minus that. No, that's that minus sinus. Yeah. So this was supposed to be minus, I guess. So we get that. And notice in particular that's bounded because the second fundamental form in n is bounded. We're assuming that n is a C2 submanifold. So HNM is less than or equal to gamma on n. At least on compact subsets. In fact, it could degenerate as you get near the boundary, near the topological boundary, but there's always some bound on each compact subset because this is a continuous function. So this is a bit, rather B is a continuous function. So this is less than gamma k on n intersect k for every compact k contained in n. So this is 1k for every compact k contained in n. So we have that. And now you simply repeat what we did before. We rearrange this using the same differential inequality computation that we worked with before. And we have to be careful about handling this term. Notice that one of the things you can certainly say is that the absolute value of this term is less than or equal to integral phi r over rho times the sup of this. So let's call that lambda. So sup mod h less than or equal to lambda. Let's call it lambda sub r on b r xi for every ball. Take a ball, send it in n, and b r xi. We've got to keep away from the topological boundary of n because n may start to degenerate if it's got a boundary. So keep away from the topological boundary, but then there'll be some fixed bound there. So then this term will be less than that gamma of r times this, as long as rho is less than r, or 1 plus epsilon rho is less than r, same sort of condition that we had before. And this is I rho again. So you can juggle these terms. I won't give the details now, but you can juggle these terms and you end up with an inequality that looks as follows. You've got to use some integrating factors this time. So it's not, the expression you get is not quite as elegant as the basic case when you've got a stationary submanifold of U, when you've got a stationary varifold in U, in an open set U. It's not quite as elegant as that, but it's not too bad. In fact, what you end up with, so similar computation. Just got to be a bit more careful in your integration. you get the following inequality. You get integral, so you get a similar kind of expression. So you get mu b rho xi, mu sub v, b rho xi over omega n rho to the n, times an exponential factor, which I'll explain in just a minute. Let's call it f rho, minus the same thing at radius sigma. That is equal to an integral, and again, there's a factor in front here, which again I'll explain in just a second. Depends on both rho and sigma, and it's the same expression as before. That is integral over the annular region between the two balls of the d r to the minus n times d per par, same expression, d mu v. And here, so whether or not that's good depends on what you can say about these things. Well, the point is that you do have control of these things because of this bound on H. And in fact, I'll leave you to check them. Details where f rho is bounded between mod f rho is less than or equal to lambda times rho over r, and mod g rho sigma is bounded once g rho sigma is positive, but it's bounded between e to the minus gamma and e to the plus gamma. So it's got fixed bounds. No problem, same bound as we got. I don't think I did this quite right. I think you've got to scale things correctly, so I think I should put a factor of r here. So r times sup over the ball of radius r of this h and m should be less than gamma. That should be the condition, so that gamma is a scale invariant quantity. So let's agree that that's the way we write the condition. So here, this is supposed to be r times sup over the ball of radius r, centered at psi, less than gamma. If we agree that that's the way we write it, then these are the results that you get. Now, let's think about that. Well, notice that this is not too bad, because here we've got e to the f sigma, which is this thing at sigma equals rho. So notice that e to the f rho then is bounded between e to the gamma times rho over r and e to the minus gamma rho over r, which is good because that certainly tends to 1 as rho tends to 0. And for that reason, you can still prove, this still implies exactly as before, that the density exists everywhere. It's not quite, notice it doesn't say that this quantity is monotone, it says that this quantity is monotone. But that's almost as good because f rho tends to 1, so you can still prove that the density exists everywhere. For every xi in n, doesn't have to be in the set M. That's for every, and it's an upper semi-continuous function. That part of the argument is very similar. Upper semi-continuous. So again, you can do what we did over here. You can give a canonical representative exactly as we did before. So everything works out. It's not quite as elegant. You've got these additional factors, but the factors are very close to 1, and you've still got monotonicity. It's just that you don't have monotonicity of that quantity anymore. You have monotonicity of this quantity. But since this tends to 1, that doesn't really upset the argument very much. In particular, you still get this. It's upper semi-continuous guy. Okay, so I wanted to mention that. So you can, I don't think it's worth going through the brutal details of this, but I just wanted to mention this fact that you can indeed, by very easy modifications of what we've done today, talk about stationarity in a submanifold instead of in an open subset of the Euclidean space. All right, so let me finish by giving a couple of, let's go back to the stationary case now. And I want to prove the convex hull property. So, consequence of stationary. So let's assume we're back in our original setting. So V equals V m theta is stationary in an open set M. In fact, let's assume, stationary in an open set U. And, in fact, let's be a little more specific. Suppose that this is equal to Rn plus K minus a compact set, K compact. And suppose furthermore that support of mu v is bounded. So in other words, there exists an R bigger than 0 with support mu v contained in BR0. So, and assume that this is stationary in this set U. Well, let's think back to the classical case. Then in the classical case, M would be a smooth minimal submanifold, and K would be something, let's take in particular, K might be the boundary of U, a boundary of M, topological boundary. So this would be one case like that, where this is a C2, M is C2, minimal submanifold. So that would be a case like this, and we would have these hypotheses in that case, right? So what could you expect in that case? Well, the claim is, in this general case, and in particular in this special case, the claim is that the support of mu v is contained in the convex hull of K. And in fact, let me just give you the proof of that. It's a trivial consequence of the monotonicity identity that we started with. So recall, well, maybe I'll leave it to next time since we're already out of time. But that's the so-called convex hull property of minimal submanifolds. In this classical case, what it's saying is if you've got a minimal submanifold with its topological boundary given by some compact set, so it's bounded, and M itself is bounded, so that's this. So M is this. Of course, this doesn't apply if M is going off to infinity somewhere. That's a different ball game. But if M is M contained in some ball PR0, and what this is saying is that the only way that can happen is if the support is in the contained in the convex hull of the compact set. So you can't have this sort of picture where you have a, say you've got a unit ball, and M is somewhere inside here, inside this ball. There's M, there's our submanifold, and suppose its boundary is on the boundary of this ball. So this is a ball of radius r, centered at the origin, say. And boundary of M contained in the boundary of the ball. That would be a typical sort of situation. Well, what this is saying is that M can't sort of have a part that comes outside the ball like that. That can't happen. It's got to be contained in the convex hull of the boundary. So I'll give you the argument for that next time. Okay.
This is kind of maximum principle.
Oh, yeah, in fact, in the classical case, you can prove this by using a maximum principle. But in the general case, you've got to use the first variation formula. Yeah. Okay, so we should stop there.